Hey everyone, this is Connor Mead with the Calculation Center, and I'm here doing another video in our calculus series. This one will be on differentiation from first principles. Now, from first principle here refers to kind of doing it a little more rigorously, going through how we derive the derivative from its definition. Okay, so in that sense, I've written out the definition of the derivative here. So the derivative is defined at a point first, and if it's defined for all points, then we say the function is differentiable everywhere. The derivative of f at a is just a real number, is defined as f prime of a, which is equal to the limit as h goes to 0 as of f of a plus h minus f of a, all divided by h. I'm going to assume you guys are kind of familiar with how limits work, just a little bit, when we're going through these, but I'll try and emphasize the reasons why the limits behave as they do when we go through some of these examples. Now, it should be pointed out here that although this definition is given relative to the point A, and it looks like it's defined for a single point, generally we're going to try and solve this problem for all possible A. So we're going to use the notation x down below, understanding that x is any one of the points on the real line. Okay. So now, given this, we're going to compute f prime of x from first principles for the following functions. And that means we have to show, basically, that this limit converges to the thing that we would expect it to. Okay? So, for example, we have f of x is equal to 3x plus 5. And we know from our kind of regular calculus that we are familiar with, this should evaluate to 3. However, we're going to go through it by applying this definition and show that this limit converges to 3. Okay? So the important thing to do for all of these is when you're evaluating the function of f of x plus h, you just look at your function f of x and replace all your x's with x plus h. Okay? So this is equal to the limit as h goes to 0. I should also point out, hopefully it's clear that we can't just simply substitute in h equals 0, because this function is not continuous necessarily at h equals 0 because of the possibility of division by 0. So we need to hopefully cancel the h or show that it goes away basically when we take the limit. Okay? So now the limit of f of x plus h here is 3 times x plus h. And f of x is, there's also a plus 5, the constant term. F of x is 3x plus 5, so we're minusing 3x and 5. And we're dividing everything by h. So this thing evaluates to, just doing the algebra, it's the limit as h goes to 0 of 3x plus 5 plus 3h, just rearranging the 3h from this, minus 3x minus 5. And we're going to divide that by h. Notice the 3x's cancel and the 5's cancel. So this thing all evaluates to just the limit as h goes to 0 of 3h over h. And the important thing, the utility of h's, or the utility of limits here, is that because we're only considering the limit as h approaches 0, h isn't actually equal to 0. So therefore it's perfectly valid to divide top and below by h, or just cancel them off. And we just get this is equal to the limit as h goes to 0 of 3, which is now a continuous function in h. So this is just equal to 3. So indeed, the derivative of f of x equal to 3x plus 5 is 3, as we expected. Okay? Now we're going to do the same thing for this function. F of x is equal to x squared. This one's going to be a little trickier, but hopefully we'll be able to go through it just the same. So let's just continue on and see if what arises. So notice that we're evaluating f of x is equal to x squared and f of x plus h, or at x plus h, I should say. So this is equal to x plus h all squared minus f of x. F of x is just x squared, so we subtract off x squared and divide through by h. And of course, we have to be a little more careful in this because we're actually taking the limit as h goes to 0. Then this is the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared. Notice that this is just expanding out the bracket here of x plus h squared, dividing through by h. The x squareds cancel again, so this is equal to the limit as h goes to 0 of 2xh plus h squared, all divided by h, which is clearly equal to the limit as h goes to 0, dividing through by h, because again h is non-zero, with limit of h as h goes to 0 of 2x plus h. And now I just want to emphasize why we're allowed to substitute in h equals 0 now when we weren't at any of the previous steps. The reason is because we've cancelled off the h, like there's no longer a h below the line, and formally speaking we say this function is continuous at h equals 0, right? Down here there was a potential that would go off to infinity when h was equal to 0, but here we see that this function is equal to its limit at h equals 0. So this is just equal to 2x, because this h term goes to 0. Okay, so indeed this has worked out again, as we'd expected. We'd have expected this to come out as 2x, because our original function was x squared. Okay, and lastly let's talk about f of x equal to 2 over x squared. So f of x, or rather f prime of x, is equal to this stuff. Let's just drag that over here, which in this context is equal to the limit as h goes to 0 of 2 over x plus h squared. Again, that's just substituting in x is equal to x plus h, minus 2 over x squared, all divided by h. Okay. To do this one now, we're going to want to try and basically, we want to be in a position where we can cancel this h. So to do that, we're going to bring these above the line. And by that I mean we're going to multiply this entire fraction, the big one, by x plus h squared times x squared, okay? That will bring these to a common denominator and move the x plus h squared minus x and the x squared below the line. So this is equal to the limit as h goes to 0 of multiplying above and below by this will give us 2x squared minus 2 times x plus h squared, all divided by h times x plus h squared times x squared. And this will be equal to the limit as h goes to 0 of 2x squared minus 2x squared minus 4xh minus 2h squared, all over h times x plus h squared times x squared is equal to the limit as h goes to 0. What do we get here? The 2x squared cancels again, so it's minus 4xh minus 2h squared, all divided by this quantity, h times x plus h squared times x squared. Notice we can cancel this first h, because each of these terms have a h in common. So this is equal to the limit as h goes to 0 of minus 4x minus 2h, all divided by x squared times x plus h squared. Now again, I want to substitute in h equals to 0 here, but we have some mild concerns in case this thing below the line is equal to 0, right? But that only occurs if x is equal to 0 as well. And to be clear, if we look at the original function, this function 2 over x squared, it looks roughly like this, and it goes up to infinity in either direction like this. Or this is more symmetrical than that, obviously, but the point is this function isn't actually differentiable at x equals 0, so we wouldn't expect it to make sense when we substitute in x equals 0. But we can say for x not equal to 0, this is equal to minus 4x over x squared times x squared, okay? Because this function is now continuous in h away from x equals 0. And sorry, this evaluates obviously to minus 4 over x cubed, which is actually, again, what we'd expect. But I just want to iterate on this point that we need to identify that x equals 0 is a problem point, so we have to exclude it from our solution. But other than that, we're allowed to substitute in h equals 0, because this function is usually continuous in h. Okay? So that's how you basically go through first principle type questions. These are generally the kind of functions you'll have to solve for. Depending on the course, of course, it might be a little trickier than this, or it might be simpler. But hopefully this made sense to everyone, and I'll see you guys next time.